Okay, so basically we are looking at this density matrix formalism of statistical mechanics. Now the main idea, okay, first we had several arguments, what is this density matrix, etc. But the main result is basically whatever we did in classical statistical physics. We had this e to the power minus beta e factors for the probability. In quantum statistics, it just becomes the Hamiltonian. E to the power minus beta, the Hamiltonian is our density matrix. There is the usual normalization. In the case of grand canonical ensemble, we have e to the power minus beta h minus mu n. Again, this is the same expression as we used in classical physics. The only difference is that here, instead of the number, we have the number operator. Instead of the energy, we have the energy operator. And these exponents, we have to take them, consider them as just the Taylor expansion of operators. So, and we did a few examples, like the free particle. We calculated the density matrix, and at the end we obtained kind of a simple result, which is at equal points. I mean, the diagonal elements of the density matrix gives us the probability, and we see that the probability of this particle to be at point R is just 1 over V. That's basically the density of the particles in our system. And R, if R and R prime are different, it kind of is related to the transition of our particle from the point R to the point R prime. And you see that it just decays in a Gaussian way. And then we had also looked at the harmonic oscillator. Well, there you need to do lots of mathematics with the Hermite polynomials, which are the solutions of the harmonic oscillators. I just skipped that. But we looked at several limits. At least now we have an understanding of what do we mean by low temperature and high temperature. It's essentially every problem has its characteristic energy scale. High temperature basically means that the thermal energy is larger than this characteristic energy scale. For the harmonic oscillator, it is h bar omega. Low temperature basically means that the thermal energy is less than that characteristic scale of the problem. Now, any questions about this density matrix? Because today, we will finish the chapter, and we will be mainly discussing what happens when we have identical mini particles. You see, on Monday, what we looked was just a single particle systems. We didn't generalize it to more than one particle. Now we will be generalizing it to more than one particle. Now, if you have, you see, a mini particle system, you can still talk about the wave function of the system. Now, of course, we basically have the same understanding that psi of psi squared is a probability that the first probability density that the first particle is at the point R1, the second particle is at the point R2, etc. So the interpretations are still the same. And we have a simple solution for this many particle system when, for example, we don't have any interactions between the particles. If we don't have any interaction between the particles, then the Hamiltonian of the system will be just the sum of Hamiltonians of individual particles. Of course, these are now operators. And formally, since we are looking at identical particles, they have the identical single particle Hamiltonian. So we can look for the solutions, eigenstates of these single particle Hamiltonians. So this is the kth eigenstate with energy epsilon k. Not that I don't put any I over there, because all the hi are identical. The only difference between the different hi's are the arguments. They are the momentum and the coordinate of the particle. Now, you see these psi k's are complete. They are the eigenstates of our Hamiltonian. So you can say that psi R1, R2, Rn, just consider the R1 coordinate. Just take all the other coordinates, if you like, as constants or parameters. So this is a function of R. But any function of R can be expanded in terms of R complete basis. So I can write this as sum over K, psi K, let me put 1, psi K1 of R1 with the various coefficients. Let me call that coefficient AK1. These coefficients depends all the other parameters. Well, I can basically do the same thing for those coefficients. So that's the function of R2. I can expand that function of R2 in terms of R complete set. So now I have K1, K2, psi K1, R1, psi K2, R2, some other coefficients, K1, K2, R3, Rn. Well, I can repeat the same thing for R3, for R4, for R5. So this n-particle wave function, I can always write it as a summation over all ki's of psi K1, R1, psi K2, R2, psi Kn, Rn of with certain coefficients. You see, since psi k are a complete set, I can do this expansion whether my system is a system of interacting particles or not. I mean, although I said that my system is not interacting at the beginning, even if my system is interacting, so I can still make this expansion. So I can expand the n-particle wave function in terms of single particle wave functions. Now, if you look at one of those terms, and act with the Hamiltonian, now I will be using the fact that I will be, at least at first, looking at a system that's not interacting with each other, a system of particles which do not interact with each other. Well, this I can write as psi k1, r1, psi kn, rn. But keep in mind that each hi acts only on the coordinate ri. So this will be, so this hi basically acts on one of the terms making that product only, the one that contains the coordinate ri, and it will give me the energy epsilon ki. So at least if my system is not interacting, this term is an eigenstate of my Hamiltonian with an eigenvalue given by the sum of the energies of each one of those particles. Well, this is not a surprise. If you have non-interacting particle, the energy of your system will be just the sum of the energies. If they were interacting, at least in classical physics, you would expect the total energy will be the sum of the energies plus their potential energy. But in quantum mechanics, it gets more complicated than that. But since we are only looking at non-interacting case, this is the total energy. Now the problem, not the problem, but kind of the problem arises, what about indistinguishability? If my particles are indistinguishable. Now, if you remember what we did in classical physics, when we were looking at the, if you remember our Gibbs paradox, we said that, okay, if we have the same particles, changing their exchanging them shouldn't give me a new state, basically because well, it doesn't give me a new state, so I have to divide by n factorial. So it was kind of an ad hoc argument, but here now we will see that where that comes from. Again, just as in when we were discussing classical, ensemble theory, remember we were looking at these numbers Ni being...
Can I ask something? Why don't we have the A factor in U?
What do you mean A?
The coefficient that you had previously when you write the wave function in terms of...
Here.
Yes.
You see, this is a general argument. Whatever n-particle wave function you have, you can write it as a superposition of energy eigenstates. Now I just looked at one of them. Well, basically now here I prove that that term, this product, is actually an energy eigenstate of my Hamiltonian, n-particle Hamiltonian.
So you're not acting on the whole...
No, I'm not acting on the whole thing. I'm just looking at one of them.
Yeah. So I was expecting a matrix.
You see, I could have just as well started from this, say that those products are energy eigenstates. But I know that if I have a Hermitian operator, energy eigenstates form a complete basis. And since they are complete basis, I could claim that I can write my wave function in terms of a superposition of them. I could also have moved in that direction. Now I'm just looking at one of them, one of the energy eigenstates. You see, if A isn't certain spatial numbers, then this wave function in general is not an energy eigenstate.
Okay.
But each one of those terms is an energy eigenstate if I ignore interaction between the particles. Now I will say that Ni is the number of particles with the wave function, let's say psi I. So this, let me call it psi B. Can be written as, well, psi 1 starting from 1 to N1 Ri times I is equal to N1 plus 1 to N1 plus N2 plus 1. Psi 2 of Ri, etc. Now these numbers Ni, of course their sum should give me the total number of particles I have, and the energy of the system can be written as Ni times epsilon I, the energy eigenvalue of this wave function. And how many such wave functions can I write? Well, exchanging Ri's gives me a different wave function, each of those Ri's. But not all exchanges of Ri's actually give me a different wave function. For example, if I exchange R1 and R2, if they are both in the state psi1, it doesn't give me a new state. So I should divide by this factor. Well, this is what we actually did in classical physics. Of course, we had the Gibbs correction. We divided by 1 over n factorial, so basically each of these wave functions had a weight 1 over n1 factorial times n2 factorial times n3 factorial, etc. Well, quantum mechanics tells us that, no, if you know the Ni, there is a single state that has that value, that corresponds to that Ni. So that was kind of, I mean, if you remember our discussions on the Gibbs factor, we said that, okay, it corrects the Gibbs paradox, but it's not the complete solution.
Can I ask something again? But this is, I'm sorry for asking this because I was focused on the previous question.
Okay.
Now I missed how you wrote the wave function. Could you repeat that?
Well, you see, this is the general wave function, right?
Yes.
Then I define these numbers Ni. I'm saying that N1 particles are in the state psi1, N2 particles are in the state psi2, etc. And well, this is one such wave function where I have N1 particles in psi1, particles from R1 to Rn, N1 are in psi1, the particles from R n1 plus 1 to n2 R n1 plus n2 plus 1 are in state 2, etc.
And B stands for bosons.
No,
No?
not yet. I haven't yet defined the bosons or fermions. B will stand for Boltzmannian.
Sorry,
Boltzmann.
boson.
So this is what we did in classical physics. We had implicitly that weight 1 over the product of ni factorials. Now, what does quantum mechanics tells us? Well, basically, quantum mechanics tells us that exchanging two identical particles shouldn't make any difference. So if I denote by P possible permutations, of particles, any one of them, I have P psi Ri. I can just consider their permutation. I can also write it as Pi. Well, I don't really care about the wave function. Wave function I cannot really observe, but I can observe probabilities. So if I permute identical particles, I should have the same state. Now, how familiar are you with permutations? Okay, let me just go over some permutations. Well, what permutation tells us is how you just change the order of numbers. So, for example, you can have a permutation which takes 1 to 2, 2 to 3, 4 to 5, and doesn't do anything. So this is, let's say, one example of a permutation. P acting on 1 will give you 2, P acting on 2 will give you 3, P acting on 4 will give you 5, P acting on 3 will give you 2, P acting on 6 will give you 6. It doesn't do anything with 6. It just exchanges, oh sorry.
So P acting on 3 equals 2. Are we reading it backwards also?
Well, that is what I am thinking about. Oh, okay. P acting on 1 go P, no, not backwards. This would be.
So P2, 3, 5 would be, so P3 and 5 would be undefined, 0.
No, this,
No.
well, the problem is this is not a permutation. This,
Okay.
so you see, permutations just shuffles everything.
Mm-hmm.
Okay.
Yeah.
This is a permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4. Four goes to 5. And 5 goes to 1. Okay. Another way of writing this is, you see, 1, we can start with any one of them. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and it's cyclic. That's just a notation. For example, I can have a permutation 1, 3, 5. What this will do is P1 will be 3, P3 will be 5, P5 will be 1, and P2 will be 2, P4 will be 4, P6 will be 6. It doesn't do anything else. It doesn't act on anything that doesn't appear there. Now, an important time of permutation is what we call the exchange. So let's say 3, 5. This P3 becomes 5, P5 becomes 3, and anything else is just itself. Well, the nice thing is I can write any permutation in terms of these exchanges. So for example, 5, 3, 1. This will be, okay, if I give it 1, it should be 3. If I give it 3, it should give me 5, but the first exchange makes it a 1. So this is 1, 5. Yes. So if I give this product 1, it will make it a 3. If I give it 2, it won't do anything. If I give it 3, the first exchange will convert it to a 1, the second exchange will convert it to a 5. If I give it a 5, the first will not do anything, the second will convert it to a 5. Well, I can also write this as 3, 1, 4, 2, 4, 2, 5, 1.
So if you give it 1 in the first line, 1 is converted to 3.
Yes.
And then 3 is converted to nothing.
3 is left by itself, so 1 becomes 3.
But in the other notation, 1 is supposed to be 5, no?
No, 1 is 3. 1 is 3, 3 is 5, 5 is 1.
Okay, right.
Okay, right. This side, 1 is 3 and 3 is 3. 3 doesn't go to 5.
No, you see, I gave it 1. I should get 3. And I do get 3.
Okay, so
If I give 3 to the right-hand side,
we don't lazy check it.
yeah.
Okay.
If I give 3 to the right-hand side, the first pay exchange converts it to a 1. The second exchange converts it to a 5. So if I give it 3, I get a 5. You see, any permutation can be written as a product of exchanges, but the number of these exchanges can change. You can have different ways of writing the same permutation. Another thing would be, for example, let's see, 3 will be a 5. If I give it a 5, it will be 3, 1. This is also the same permutation. It can look different. The number of exchanges can be different. But what will remain the same is the number of exchanges that is required to write a given permutation will always remain either even or odd. You see, here I have 3 cases. I can write it in terms of 3 exchanges, 4 exchanges, or 2 exchanges, 4 exchanges, or 2 exchanges in a different way. So they're all even. That's what we call an even permutation. In other cases, it can be an odd. So it will be an odd permutation. So I can, in a sense, divide the permutations into even and odd permutations. So, so these are the notations. So let's go back to our wave function. I know that. And keep in mind that this is just a product of an exchange. So you just apply the exchange twice. Or you can say that you are taking the square. This is just identity permutation. It doesn't change anything. So let's say, if you apply an exchange on our wave function, nothing should change. So if I apply the exchange twice, again, nothing should change, because this is identity. So if I look for an eigenvalue of these exchange operators, well, basically the second one tells me that lambda squared should be 1. But if well, the first one basically tells me that absolute value of lambda should be 1. The second one, sorry, I don't even have the absolute values over here. The second one tells me that its square is not just the absolute value, its square has to be 1, which tells me that lambda should be plus or minus 1. Okay, so on one hand, I'm saying that if I exchange identical particles, nothing should change, which is basically telling me that the exchange operation is a symmetry of my system. And so I can write down the eigenvalues of the Hamiltonian. I can always write them as eigenvalues of these eigenfunctions of these exchange operators, which are plus or minus 1. So the eigenvalues of my n particle system, when I apply with an exchange operator, should be, you see, plus or minus my wave function. And in fact, that plus or minus is basically given by minus 1 to the p. This is the notation. Plus or minus p is called the signature of the permutation. Is equal to minus 1 to the p is called the signature of the permutation. Plus 1 to the power p is always plus 1. Minus 1 to the p is plus 1 if p is an even permutation. And minus 1 if p is an odd permutation. So basically, we can distinguish identical particles. We can classify identical particles into two groups. Those who don't receive any sign when you exchange a pair of identical particles. Those are what we plus 1 to the p. These don't change if you just exchange into two pairs. These are called bosons. And then we have those particles, those wave functions which exchange their sign when you exchange the identical particles. Those are called our fermions. This is general for an arbitrary n-particle wave function. For fermions, it has to be antisymmetric under the exchange of any two of the arguments. For bosons, it has to be symmetric. Now, how do you decide whether a given particle is a fermion or a boson? Well, that is called the spin statistics theorem. Which states that particles with integer spin are bosons, and particles with half-integer spins are fermions. Well, the proof requires some basic knowledge of field theory. The basic idea is for fermions, if you assume them to be symmetric, the energy turns out to be unbounded from below. So if you want to bound the energy from below for fermions, you have to make sure that if the wave functions has to be antisymmetric. The reason why the energy becomes unbounded basically turns out to be related with the fact that the wave function for fermions, it satisfies the first order, a differential equation that is first order in time, whereas for bosons, it's second order in time. Anyway, so let's try to impose this condition on our wave function. You see, we started looking at these product wave functions. Which I call Boltzmannian. Obviously, they don't satisfy this condition unless all the particles are in the same state. So we have to symmetrize or anti-symmetrize them. So the wave function, whether it's symmetric or anti-symmetric, we can write it in this form. Plus or minus 1 to the p. I will sum over all possible permutations. Plus or minus p of, let me write it explicitly K1 R1 K2 R2 psi Kn Rn. Now, of course, I have to exchange all the positions of the particles. So this is whatever this permutation takes, 1, 2, and n2. So this is my unnormalized. I haven't normalized the wave function. But that's my wave function, and we definitely know that if you take the minus sign over there, -1 to the p, then it is anti-symmetric under the exchange of any 2. If you take the plus sign, it will be symmetric. Okay, so when you do it for n particles, it's kind of, I mean, it's what we are doing might not be so obvious. So I would try to go side by side, the n particle treatment and the 2 particle treatment. So what are we talking about when n is equal to 2? Well, if you have 2 particles, we have basically 2 permutations. P1 is nothing. It doesn't do anything. P2 is this one. It just changes 1 and 2. So the symmetric wave function will be sum over P psi K1 R P1 psi K2 R P2. Remember, these K1 and K2 are all the quantum numbers of these wave functions. There is no, the factor is +1 to the P, which is +1. Well, which will be psi K1 R of P11 psi K2 R of P12 plus psi of K1 R of P21 psi K2 R of P22. Well, P1 doesn't change anything. The first permutation. This is R1. This is R2. P2 just changes 1 and 2. So this is our symmetric wave function. Now, in the case of antisymmetric wave function, if these are fermions, I should introduce this -1 to the P, psi K1, R of P1, psi K2, R of P2. Well, the only difference from the previous computation is that now I need to insert the signature of the permutation. Identity permutation is just the trivial permutation, so it's just, it has a signature 1. P2 permutation is, well, let me write this as 1. P2 has a signature -1. You see, if we just exchange R1 and R2, the first terms just become the second terms become the first term. The symmetric wave function, nothing changes. In the anti-symmetric wave function, due to this relative minus sign, it just acquires a minus sign. And another thing you should see, if you have these anti-symmetric wave function, this is equal to 0 if K1 is equal to K2. If K1 is equal to K2, the first term is the same as the second term. So those 2 particles cannot be in the same state. There is no such restriction for the symmetric wave functions. If K1 and K2 are equal, well, no problem. But in the second case, if K1 is equal to K2, the wave function is 0. Basically, there is no such state. So that is why we say that you cannot have more than one fermion in a given state, because the wave function is anti-symmetric, has to be anti-symmetric. For bosons, there's no such restriction. Now, just another thing to note is if you look at sum over all permutations, minus 1 to the p psi k1 r of p1 psi k2 r of p2 psi kn r of pn. This is actually a determinant. This is the determinant of this matrix, psi k1 r1 psi k1 r2 psi kn rn psi kn r1 psi kn r2 psi kn rn. No, sorry. This is 1. So exchanging two particles just corresponds to exchanging two columns of this determinant, and if you exchange two columns of a determinant, it just changes sign. Are any questions up to here? So you see, once we know these ni's, the number of particles in a given state, in that case we know how many psi ki is in this product, in these products over there. And once we know how many psi ki's are in that product, well, there's a single state that has that many ki's in each one of those products. So once you know the ni's, there is a single microstate corresponding to those numbers ni. So now, question? Now okay, we know our wave functions now for the n-particle systems. For fermions, it will be antisymmetric. For bosons, it will be symmetric. What about the density matrix? Let's calculate the density matrix corresponding to the system. Well, let's say rho. Let me start with e to power minus beta h bar. And note that I didn't yet normalize it, because I will define rho as I will try to calculate R1, Rn so this will be basically the normalization of the states cancels in this ratio. So that's why I don't really care about the normalization of the wave functions yet. So let's look at this one. Well, this will be, well, the bra will be minus 1 to the p. Let me introduce the energy eigenstates first. Times e to power minus beta sum over epsilon ki Sum over all possible ki. Now, what are these ki's? Ki's, if I use periodic boundary conditions, it will be 2 pi over L Ni. Ni's can take values 0, plus minus 1, plus minus 2, etc., up to infinity. And epsilon ki is just h bar squared k squared over 2m. It's the kinetic energy. Now I need to evaluate this sum. Well, I know those matrix elements. The left-hand side, it will be, let me write it as a sum over p minus 1 to the power p e to the power I minus I k I r of pi the right-hand side, again, a sum over all possible permutations. Let me call it p prime minus 1 to the power p prime of product over I e to the power I ki dot r of p prime I. Times e to the power minus beta epsilon ki. This is also prime. Okay, the first thing I will do is let me move that permutation from the coordinate to momentum. Well, you see, if for two particles, if you look at the first product, it is K1 R1 plus e to the power minus I K1 R1 K2 R2 plus or minus e to the power minus I K1 R2 plus K2 R1. But this is the same thing as e to the power minus I K1 R1 plus K2 R2 plus or minus e to the power minus I K2 R1 plus K1 R2. I just changed this term became this one, this term became this one. So rather than permuting the coordinates, I can permute the case. It's the same thing. That's the idea. Now, this is something I hated when my professors used to just erase on the board and just change the positions, because I had to write it down from scratch. Now, the second thing I will say is that, you see, if you look at that product, I have many cross terms. But since in each one of those sums, I'm taking into account all possible permutations, there will be many terms that are identical to each other. And in fact, I can just write this as sum over K1 You see, if I have n terms, I can consider n factorial possible permutations. And in fact, this summation over p prime, each one of those terms will basically contribute the same thing. Do you see it or don't you see it? Now let's look at this term for two particles. This is one of the sums. Well, the other sum is actually identical, except on the change in the sign. And the positions are now prime positions. Okay. So I have this product for two particles. So let's see. I have the first two terms, a to the power I, k1 dot r1 prime minus r1, and plus I k2 times r2 prime minus r2. Okay. The product of the second terms plus a to the power I k2 times r1 prime minus r1 and a to the power minus I k2 times k1 times r2 prime minus r1 r2.
The minus sign, right? This exponent. This exponent will have a minus.
Well, let's see. K2, no. R1 prime minus R1, R2 prime minus R2, no. So this is the first, this one is the first term times the first term. This is the second term times the second term. And remember, I'm summing over all K1 and K2. So I can just, K1 and K2 is kind of a dummy index. So I can just, in each sum, I can just rename them. But if I rename them, this is K1. This becomes K2. Again, I say, I emphasize, I'm just renaming them. You see, they are the same term. The contribution of the first term in this second part and the second term in the second part is the same. Of course, you have to look at the 1 times 2, 2 times 1, the cross term, but it will basically be the same. So just take the first term, the second term basically contributes the same. So in the second term, I don't need to take into account the permutations. I just need to know how many permutations I have. So that is why in the second p prime sum, I don't consider any permutation. I just look at the contribution of the identity permutation. Because all p primes will contribute equally. And there are n prime contributions. So that's why now I have this n prime over here. Right, this is the Boltzmann that gives correction and factorial. We will see. We will come to that.
Are the explanations correct? Are the explanations correct?
Why?
Between, if I split it down the middle from the plus sign, they're all the same.
Yes, that's what I'm saying. They are the same.
Okay.
That's my argument. You see, the first one is the contribution from this term. The second one is the contribution from the second term. And I claim that they are the same. So I didn't need to calculate the contribution from the first term in that second line and the second term separately. They are the same. So I will just calculate the contribution from the first term from the second line and multiply by 2. Because there are only 2 permutations. If you generalize it to n permutations in this summation over here, well, look at the p prime summation, that is the second term. Each one of those terms will contribute the same. Basically, because of 2 reasons. In the first sum, I have all p's, and at the same time, I'm looking at I'm also summing over all ki's. So since each one of those terms will contribute equally, I just calculate one of them, which I choose to be the contribution from the identity permutation for p prime, and multiply it with the number of permutations I have, number of terms I have in that p prime summation. And since I have n prime permutations of n numbers, well, I just multiply it by n factorial. Okay, let's give a break here, and then we will continue after the break.